So now that you've learned what L'Hopital's rule is, and let me just summarize it very quickly for you. L'Hopital's rule tells us that the limit as x approaches some value, we'll call it c, of f at x over g at x is equal to the limit as x approaches c of the derivative of f at x over the derivative of g at x. Now there are a couple conditions for when we're allowed to use this. We're only allowed to use this rule if, when we originally try and evaluate the limit as x approaches c of f at x over g at x, if we get indeterminate form of type 0 over 0 or infinity over infinity. So that happens if the limit as x approaches c of both f at x and g at x are both 0, or if the limit as x approaches c of f at x is plus or minus infinity, and the same with the limit as x approaches c of g at x. So now that you remember what L'Hopital's rule is, and when we're allowed to use it, right? We're only allowed to use L'Hopital's rule, and I've got it summarized down here. We can only use L'Hopital's rule when we have indeterminate form of type 0 over 0 or infinity over infinity. But there are many other indeterminate forms you might get when trying to evaluate a limit. If we look at all these indeterminate forms, 0 times infinity, infinity minus infinity, 0 to the power of 0, 1 to the power of infinity, and infinity to the power of 0. Those are all indeterminate forms. All of those forms don't tell us what the limit is, and they also don't even tell us if the limit exists. But for those forms, we're not allowed to use L'Hopital's rule. But there are some tricks to rewrite the functions so that we end up getting indeterminate form of 0 over 0 or infinity over infinity. So I'll say we'll try and rewrite these functions so that you get 0 over 0 or infinity over infinity, and then use L'Hopital's rule. So let me show you each of these other types of indeterminate forms, the ones that I've highlighted in blue. In the previous video, I went over the ones highlighted in red, the typical L'Hopital rule examples. These ones are going to be a little bit more challenging because we're going to have to do some rewriting before we can use L'Hopital's rule. Let's start by looking at the indeterminate product 0 times infinity. So if the limit of f at x as x approaches a is 0, and the limit of g at x as x approaches a is plus or minus infinity, then the limit of their product is called indeterminate form of 0 times infinity. What we can do to try and make it be indeterminate form of 0 over 0 or infinity over infinity is rewrite the product in this way. If we have f at x times g at x, there's a couple tricky ways we can rewrite that same product. We could rewrite it as f at x over 1 over g at x, or g at x over 1 over f at x. Depending on which variations of those we use, we'll either get type 0 over 0 or infinity over infinity when we try direct substitution, which would then allow us to use L'Hopital's rule. Let me show you how that works. So for example 3, we want to evaluate the limit as x approaches 0 from the right of x times ln x. Well, let's look at the limit of each of those functions. I know this would be equal to, based on limit rules, this would be equal to the limit as x approaches 0 from the right of x times the limit as x approaches 0 from the right of ln x. Well, I know that as x approaches 0, x is going to be 0. And as x approaches 0 from the right, let's look at what ln x would be approaching. We could choose a test value, or I know what the graph of ln x looks like. Ln x has a vertical asymptote at x equals 0. It looks something like this. So I know for this function, as I approach 0 from the right, so let me just approach 0 from the right, the screen section here, I'm approaching the x value of 0 from the right, the function is going infinitely low. So I know the limit of ln x as x approaches 0 from the right is negative infinity. This is an indeterminate form. This doesn't tell me if the limit exists or not. So what I'm going to have to do is try and rewrite this function, and I'm going to rewrite it in a way so that I can use L'Hopital's rule. I'm going to rewrite this as the limit as x goes to 0 from the right as ln x divided by 1 over x. That's equivalent to x times ln x. I'm just writing it as a quotient. And now if I were to look at the limit of each of these functions, so if I look at the limit of ln x as x approaches 0 from the right, well, we already established that that's going to be negative infinity. But what happens to 1 over x as x approaches 0 from the right? Well, what does 1 over x look like? 1 over x looks like this function, this hyperbola. As I approach 0 from the right, that would be this section of the graph right here, it's going off to positive infinity. So I know the limit of 1 over x as x approaches 0 from the right is infinity. So now I have indeterminate form of negative infinity over infinity. So that meets the criteria for being allowed to use L'Hopital's rule. So I can erase this indeterminate form, and I can differentiate the function in the numerator and the function in the denominator, and the limit will be equivalent. So I can say this equals the limit as x approaches 0 from the right. The derivative of ln x is 1 over x. And the derivative of 1 over x, I actually like to think of 1 over x. I'm going to rewrite that as x to the power of negative 1. I find that easier to differentiate. The derivative of x to the negative 1 is negative x to the negative 2, which I could rewrite as negative 1 over x squared. And now let me simplify this quotient I have when dividing fractions. I can multiply by the reciprocal of the denominator. So I have 1 over x times negative x squared, which just gives me negative x. And now if I use direct substitution, I can just sub in 0 for x, and I get 0. So the limit as x approaches 0 from the right is 0. Let's now try when we have an indeterminate difference. So what if the limit of f at x and g at x as they both approach a are both infinity? That would mean that the limit of f at x minus g at x as x approaches a, we would get the indeterminate form of type infinity minus infinity. Once again, that doesn't tell us if the limit exists or not and doesn't tell us what the value is. So we will try and rewrite the difference of the functions in a way so that we would be able to use L'Hopital's rule. Let's look at both of these functions and see that if we tried direct substitution, we would in fact get the indeterminate form infinity minus infinity. For these types of questions, I like to look at the limit as x approaches 0 from the right of each of the functions separately. So 1 over sine x minus the limit as x approaches 0 from the right of 1 over x. And we could do this with test values, or since these are easy graphs to understand, let's just look at the graphs of these. So first of all, the graph of sine x. You know what the graph of sine x looks like. The graph of sine x, not a great sketch of sine x, but you can see that sine x, as x approaches 0 from the right, sine x is approaching 0. So I'm getting 1 over a function that's approaching 0 from the right, which is going to give me an infinitely large value. So this is going to equal infinity minus, what does 1 over x look like? 1 over x looks like this. As I approach 0 from the right, 1 over x is going off to infinity. So this gives me indeterminate form of infinity minus infinity. When we get that indeterminate form, we don't know if the limit exists or not, but a good strategy would be to try and rewrite the difference of the functions as a quotient of functions, and then maybe we'll be able to try using L'Hopital's rule if we get indeterminate form of infinity over infinity or 0 over 0. So let's combine the functions that are being subtracted with each other by getting a common denominator. Let's multiply 1 over sine x by x, top and bottom, and multiply 1 over x by sine x, top and bottom. So this would equal the limit as x goes to 0 from the right of x minus sine x all over x times sine x. Now if I tried direct substitution, I would have 0 minus sine of 0, and sine of 0 is 0, so I have 0 minus 0 over 0 times 0. So this is indeterminate form of 0 over 0. When I get that, I know I'm allowed to use L'Hopital's rule. So I can erase this direct substitution, and I can try using L'Hopital's rule, which tells me I can differentiate the function in the numerator and the function in the denominator, and the limit will stay equivalent. So I can say this equals the limit as x approaches 0 from the right of 1 minus cos x over the derivative of the function in the denominator. I would need product rule for. The derivative of x is 1, multiply that by sine x, plus the derivative of sine x is cos x, multiply that by x. And now let's try direct substitution and see what happens. If I sub in 0 for all the x's, I'd have 1 minus cos of 0 all over 1 times sine of 0 plus 0 times cos of 0. I would get, well, cos of 0 is 1, so I'd have 1 minus 1 over 0 plus 0. So I'd have, indeterminate form of type 0 over 0 again. So when that happens, I'm going to backtrack. I'm going to erase my direct substitution. And because it's type 0 over 0, I know I'm allowed to apply L'Hopital's rule again. So with L'Hopital's rule, I can once again differentiate the function in the top and the function in the bottom separately. So the limit is still going to be equal as x approaches 0 from the right of the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator, well, the derivative of negative cos x is sine x. In the denominator, the derivative of sine x is cos x. Plus, I'm going to need product rule when I do the derivative of cos x times x. The derivative of cos x is negative sine x. That has to be multiplied by x. Plus, the derivative of x is 1. That has to be multiplied by cos x. I can collect some like terms in the denominator. I have a cos x plus a cos x. That's 2 cos x minus x sine x. Now if I try direct substitution, let's see what happens. I would have sine of 0 over 2 cos of 0 minus 0 sine of 0. Well, sine of 0 is 0. Cos of 0 is 1, so 2 times 1 is 2, minus 0. So I have 0 over 2, which is equal to 0. So I've found the limit. The limit as x approaches 0 from the right is 0. The last type of indeterminate form we're going to look at is indeterminate form of type 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity. All of those are indeterminate forms that we wouldn't directly be able to use L'Hopital's rule with those, but we could apply some tricks to be able to rewrite those powers in a way so that we get indeterminate form of type 0 over 0 or infinity over infinity. And the way we do that is by taking the natural logarithm of both sides. That's going to allow us to get the exponent into the coefficient of our function. And then we'll be able to use L'Hopital's rule once we get it written as a quotient. Let me show you what that's going to look like with this limit here. So I see I have the limit of a power. So if I try direct substitution, if I get any of these three formats, I know I'm going to then take the natural logarithm of both sides and then try and manipulate it to be able to make it into indeterminate form of type 0 over 0 or infinity over infinity. So let me see what happens if we do direct substitution first. So if I sub in 0 for these x's, I get 1 plus sine of 4 times 0, all to the power of cotangent of 0. Well, sine of 0 is 0, so the base of the power is just 1. And cotangent of 0, as I approach 0 from the right, well, cotangent, we could pick a test value, or if we know what this function looks like, cotangent I know kind of looks like this. So as I approach 0 from the right, I can see that the function is going off to infinity. So this would be 1 to the power of infinity. That's indeterminate form. Doesn't tell me if the limit exists or not, so I have to erase that. The trick when we get that indeterminate form is to actually, let's just name the original function. Let me just say f at x equals the power 1 plus sine of 4x to the power of cotangent x. Now I want to get that cotangent x out of the exponent, so I'm going to take the natural logarithm of both sides of this equation. And then the power rule of logarithms tells me that I am allowed to take the exponent of the argument and write it as the coefficient of the logarithm. And I know I want the limit as x approaches 0 from the right, so let me find the limit of both sides of this equation. So the limit as x approaches 0 from the right of ln of f at x equals the limit as x approaches 0 from the right of the whole right side of this equation, that product of functions. Now on the right side of this equation, I would have indeterminate form of infinity times 0, and we learned in a previous example that if I rewrite the product as a quotient, I may be able to use L'Hopital's rule. So I'm going to rewrite cotangent x times ln of 1 plus sine 4x as ln of 1 plus sine of 4x divided by 1 over cotangent x. And 1 over cotangent x just means the reciprocal of cotangent, which is tangent. So I'm just going to, instead of writing 1 over cotangent, I'm just going to write tangent. Now if I tried direct substitution on the right side of this equation, I would get ln of 1 over tan of 0. Well, ln of 1 is 0, and tan of 0 is 0. So now this is indeterminate form of type 0 over 0. So when that happens, we're allowed to use L'Hopital's rule. So I'm allowed to go ahead and just differentiate the function in the numerator and the function in the denominator, and then try direct substitution again. The derivative of ln of 1 plus sine of 4x would be 1 over 1 plus sine of 4x times ln e, which I don't have to write because that's 1, times the derivative of 1 plus sine of 4x, which is 4 cos of 4x. And this is all over the derivative of tan x, which is secant squared x. Let me just rewrite that numerator with the 4 cos of 4x up in the numerator. And remember secant squared is actually 1 over cos squared. I'm writing it like that because now that I have a fraction divided by a fraction, I can multiply by the reciprocal. Okay, and now let's try direct substitution on the right side. So I would have 4 cos of 0 times cos squared of 0 all over 1 plus sine of 0. That's 4 times 1 squared all over 1 plus 0. So that's just 4. So remember, what I have found here is not the limit of f at x as x approaches 0 from the right, but this is the limit as x approaches 0 from the right of ln of f at x. But what do I actually want? I actually want the limit as x approaches 0 from the right of f at x. Right? I want it of the original function, which I named f at x way back at the start of the question here. So what I'm going to have to do is one more little trick. I'm going to rewrite f at x in a little bit of a tricky way. I could rewrite f at x as a base e power. I could write it as e to the ln of f at x. That's just equal to f at x. Right? Let me just write a rule up here. B to the power of log base b of x is just x. So based on that rule, I know that this is just f at x. So that's why I'm allowed to say that these are equivalent, because f at x is the same thing as e to the power of ln of f at x. And why did I write it like this? Well, because if we look carefully at what we have in the exponent of e, it's ln f at x. And I know that as x approaches 0 from the right, ln of f at x is going to 4. So I know that this limit, as x approaches 0 from the right, will be going to e to the power of 4. And there's my final answer. Jensen Math!